whenever you're ready.
Okay, now you're I'll try to like stay near you.
I think we should wait till they're here.
Yeah, all right, we got it.
A couple more coming now. We should wait till they're here, I think. Just another minute.
All right. I think we're probably
You're good, you don't have a link.
good to get started. So welcome to the Atmospheric and Oceanic Sciences Faculty Flash Talks. So today we'll be hearing from 6 different members of the AOS community about some of the research that they do. Talks are going to be about 8 minutes, and then we'll have a 1 to 2 minute period for Q&A following each talk. So I'll start by introducing each speaker, and then we'll hear their talk. For the speakers, I'll give like a little sound signal when you have about a minute left. Yeah, and that's kind of all I had there. So to start us off, we have Dr. Hannah Zanowski. So Hannah's lab explores the physical oceanography of Earth's polar regions using coupled climate models. She is particularly interested in Antarctic bottom water formation and its connections to deep ocean variability. Meet the Zanowski lab.
Can you hear me all right? Or should I put this? Okay, yes, good. All right, so thank you, Bailey, for my lovely introduction. I have a lab now. I have 1 undergraduate student. I'm so proud of myself. So I started here about 6 months ago now, and I'm a polar oceanographer. So obviously that means that I study Earth's polar regions. So to kind of set the stage for you, I look at the Antarctic and I also look at the Arctic. The Antarctic is basically land surrounded by the Southern Ocean. So this would be kind of your ice sheet that sits over Antarctica. We have a bunch of sea ice here as well. And so the Antarctic is really a wind and buoyancy driven regime. So you have a bunch of heat exchange through the sea ice and with the atmosphere, as well as some pretty awesome ocean circulation that happens within this region. And the Arctic is sort of the reverse of that, but not really, in the sense that it is actually an ocean, a sea ice covered ocean surrounded by land. It is actually also a wind and buoyancy driven situation, but in this case that buoyancy has more to do with sort of riverine inputs and freshwater inputs that drive a lot of what happens within this region. And so again, they host fairly complex circulations, both of them. The major kind of current that you see in the Antarctic is the Antarctic circumpolar current. Kind of flows clockwise around the Antarctic continent and kind of keeps this region relatively isolated from the rest of the planet. And then in the Arctic, you have sort of various flows within the Bering Strait, and then in these kind of complex passages in the Canadian Arctic archipelago, and a bunch of sort of interactions, if you will, with the North Atlantic Ocean. And so, even though these regions are kind of across the globe from each other, they are fundamentally coupled systems, right? You can't I like to think about the oceanography part of them, but they are sort of connected, of course, to the sea ice, to the atmosphere, to all of these different things, the land ice that's happening within them. And so they tend to be really, really rich, interesting, dynamical places. So can you advance for, cool, okay. And they are actually connected to each other through the overturning circulation in the ocean. So this is a very, very chill schematic of the overturning circulation in the global ocean. And in the North Atlantic and around the Antarctica, you have dense water formation regions. Where Google happens? Oh, you're fine, don't worry about it. Where water kind of sinks and spreads out into the very deep parts of the ocean. And that's where these things are kind of connected. We have North Atlantic deep water that eventually ends up upwelling in the Southern Ocean. And we've got these two sort of limbs to the circulation. And so, go ahead and step forward. And so for me, I study the polar oceans because I want to understand the processes that drive polar ocean variability, and also to kind of understand how changes in these regions are then communicated globally through these deep and bottom waters that kind of sit in the lowest parts of the ocean. Uh-oh, that got crazy. I don't know what's happening here. That's not supposed to look like that, but anyway. Anyway, that's supposed to be my beautiful coupled climate model. So I use global general circulation models to understand how the ocean works in these regions. And so these are really kind of complex systems where you bring in the atmosphere, the ocean, the ice, the land itself to kind of understand what our planet looks like and how it will change in the future. Models are a tool, though. They are right and they are wrong at the same time, but they are the only thing we have for really looking into the future if we want to know something about how things are going to change. And this picture is the very first iceberg I ever saw. John, this one's for you. I cried when I saw this because when you see an iceberg and you stand in the presence of greatness like that, you will cry. It's a really amazing experience, so go forward, please. So some of my recent work is actually not Antarctic. Man, what is happening here? Okay, well this is going to be really hard to show you because nothing's actually showing up like it's supposed to.
Are these supposed to be animated?
No, they're supposed to actually have like beautiful colors on them. Like they're supposed to be bars here. Well anyway, this is turning into an unmitigated disaster. So pretend like you can see this properly. Recently I've been looking at the freshwater in the Arctic Ocean. And so freshwater is basically a way for us to understand the state of the Arctic Ocean and how it might change. And so I'm talking about either water that doesn't have any salinity in it or water that's relative to a certain reference salinity. And what I've done here is I'm looking at a bunch of different coupled climate models that have kind of been part of the most recent model intercomparison project to kind of understand what kind of mechanisms are at play for this freshwater. And I really kind of can't explain these figures because I do not know why they look this bad right now. So there's supposed to be a bunch of really pretty colored bars here to kind of compare across these models, but they're not here. But at any rate, we can kind of look basically over the historical period, so from 1988 all the way to 2100 to kind of understand how things are changing in a couple of different future forcing scenarios. So we force these models with different ideas of what the future might look like to kind of understand how things might change. So I'm just gonna just keep moving forward because this is not good. But okay, well this one turned out better. Okay, all right, so it's just the Arctic one that's an unmitigated disaster. So besides my Arctic work and then kind of thinking about freshwater, I also have a couple of other interests in irons in the fire. I always do. So I call myself a polar oceanographer, but I think about lots of different kinds of oceanography. And so right now I have a paper in revision that uses paleoclimate model simulations to understand past deep Pacific Ocean circulation change. And I'm talking about from the last glacial maximum, so about 22,000 years ago to the present day. And we can use various tracers like carbon-14, which is an age tracer, to kind of tell us about that circulation and compare it to other tracers within these regions. They can kind of say something about how the ocean has evolved over these very, very long time scales as well. And then compare them to sediment proxy records to see if we're actually understanding how things have changed. Recently, actually over the past few years, I'm really interested in getting involved in icy worlds oceanography. So there are multiple oceans within our own solar system, and there are even more outside of it. icy worlds, Enceladus, Europa, Titan, Triton, Callisto, Ganymede, they all have subsurface oceans. And this makes me really, really excited. NASA's also very excited about it too. I've been part of a planetary origins of life cluster hire on campus here, where we're kind of starting to think about habitability, origins of life as related to ocean worlds and exoplanets in general. And again, NASA's on board with this. They are sending a mission to Europa in 2024 it takes off, so it's actually happening. And even today at the Ocean Sciences meeting, I got to see NASA share 2 potential mission concepts for landers on Enceladus and Europa to kind of start to think about what these oceans and these icy worlds actually look like and whether that's the harbor life. So that really excites me. Next slide, please. And then the other thing I always like to talk about is to do a lot of other things besides research. Research is an important part of what I do, but it is not my be-all, end-all. I teach. Obviously, I'm a professor. Right now, I just teach AOS 573, which is a graduate class on computational methods in atmospheric and oceanic sciences. Am I doing good or what? Okay, cool. Where basically I teach Python for how we do our jobs. Super hands-on class where you get to learn all of the different kind of techniques that we use for data analysis within our field in atmospheric and oceanic science. I am also leading the charge on this inaugural AOS undergraduate summer research program. So this summer we're going to host 5 interns to come do research with us as sort of a test bed for potentially or eventually kind of hosting a real REU here. So I'm going to just leave it at that. Sorry about the figures getting real wonky there. If you have any questions, please feel free to ask. Yeah.
So I don't know if I interpret this right, but it looks like during a bowling Alrod period, you have an increase in the age of water in the bottom of the Pacific, but isn't that when the overturning circulation speeds up? But I'm probably misinterpreting it.
That's not, when the ages are getting older, the overturning circulation is slowing down.
Yeah. So,
Yeah. So
is that going from the VA to the younger dryas? Is that the slowdown? I guess so.
Depends on where you're looking. No, so this would be an increase, right? So the age goes up,
Yeah.
and that means the circulation slows down. But with carbon, you have to be a little careful in how you interpret it. That's the point.
Any other questions for Hannah? Thank you.
I'm so sad. Sorry, I
Yeah, I didn't do that. I'm not going to worry.
Oh, it's back here. Well.
All right, so our next speaker is Dr. Jon Martin. Jon's lab focuses broadly on synoptic meteorology and large-scale dynamics with interest in tropopause level jet streams and cyclone structure.
Thanks, Bailey. And we've been doing other things too. We kind of stumble into some climate problems here and there, and this is one that I'm kind of interested in. I'm really excited to talk to Ángel about this. We never really got a chance to do it, but I've got some ideas about the transition from winter to spring in the Northern Hemisphere and the circulation changes that accompany that transition. And in the fall, that transition from summer to fall or fall to winter can be populated and affected by recurving tropical cyclones, which when they get to higher latitude, they're sort of diabatic features, and they have implications in the flow as a consequence of that. I think there's something similar that might be underlying differences between winter to spring transitions in various years, and that focuses on features known as tropopause polar vortices. And these are features that develop during the Arctic night as a consequence of cooling over stratus clouds. So you can have land underneath and you have a low stratus cloud deck in the Arctic. There's no incoming solar radiation, so all you have is diabatic cooling. We go to the next slide. And above that cooling, because of the gradient of diabatic heating, you can produce positive PV anomalies. So we can go to the next slide. The tropopause is depressed above the cooling regions. And so this is one way to produce, in the Arctic winter, upper level tropopause positive potential vorticity anomalies, which, if they get their way into the mid-latitudes, become the seeds for the development of mid-latitude cyclones. So let's see the next slide. gives you an idea. I got displaced here. This is
Yes.
a little bit wrong.
Now I feel less bad.
This is supposed to be in the middle of the box, and this is a population of these diabatically generated TPVs. And so the next slide shows what happens if you have, what happens if you get a high amplitude flow in the middle of the wintertime? Well, some of the TPVs on the southern periphery of the region where they might exist might get ingested into the mid-latitude flow. When they do, they become agents for development at sea level. So that's kind of one of the interesting things that happens during the winter. What I'm thinking about is, we can go to the next slide, not all of these TPVs get connected to the mid-latitude flow. And in fact, at this time of year when the sun's coming up, since they had a diabatic origin, they run the risk of elimination by the very same process. The sun comes up, they're going to be eroded. So how do we get these things that are formed over the Arctic night out of the Arctic? Or do we do it equally from year to year? And if we do it preferentially in some years, are those years more stormy in the spring than others? And so that's the difference in the spring, the transition into spring. So that's what I'm thinking about. What's the difference year to year in storminess? How do you measure that? Let's go to the next slide. So here's one way you could do it. You could just take an annulus, 65 to 25 degrees north latitude, and then just in this region, calculate the aerial extent of a bunch of thresholds of 1,000 millibar geopotential height. Minus 32 meters, all the way to minus 224. This is like 996, 992, 988, and so on, in terms of sea level pressures. So a stormy spring will be one that has a lot of area in these 7 categories, and a less stormy spring will be one that just doesn't have as many cyclones and not as many intense ones. So it's simple-minded, but that's the way I'm thinking about it. So let's go to the next slide, please. Here's the long-term average from the NCEP reanalysis data from December 1st to the end of April of the minus 32 meter line. So this is 996 millibars, this is 984, 972. You can take any given year, I've been looking at February 15th to March 15th, superimpose it on top of this in all 7 of the lines, and I'm only showing you 3, and then just add up the departures from the long-term average. And by doing that, you can rank the years in terms of storminess. And so that's, again, simple-minded, that's what I'm doing. So let me show you what I have. When I do that, we can go to the next slide, Bailey. When I do that, I take the 5, I think how many years? 5 stormiest years, by that measure, from February 15th to March 15th, and then the 5 least stormy years. And I do a difference on the average geopotential heights and sea level pressures and so on in a variety of heights. This is the difference between the stormiest and least stormy years in terms of sea level pressure. Contour intervals 4 millibars. And this is a depression, this is an anticyclone. So there's a deep Aleutian low in years that are stormier in February to March. And there's not really a deeper Icelandic low, so it's kind of biased toward the Pacific. Let's go to the next slide. These structures are roughly equivalent barotropic. So this is the 500 millibar height field. There's an elongated trough across the northern part of the Pacific Ocean, and a little bit of a trough here at the Labrador Sea, and some troughiness also over the southeast United States. And that geopotential height field has consequences for the near tropopause level flow. So if we can go to the next slide, that's the 300 millibar wind speed differences. And so you get an extended jet. This is Hawaii. This is about the date line. So further here, I guess. And so the jet is wildly extended almost all the way to the west coast in stormy years compared to non-stormy years. And you have a stronger subtropical jet across the Gulf of Mexico, although that's only modestly so. Much stronger Pacific jet and wildly extended. So the question is, let's go to the next slide. Where are these TPVs at this time of year? And this is a diagram that comes from my colleague Stephen Cavallo at the University of Oklahoma. It's a March TPV probability anomaly. So as I understand it, that means that if you're over this part of the Eurasian continent, you have 10% higher than usual number of TPVs for that time of year. Well, I should say that time of year has a 10% higher probability of TPVs existing there than other times of year. So that's how you read this diagram. So they seem to be biased towards central Eurasia and then north of the archipelago in our hemisphere. If I superimpose the 500 millibar height field on here, which is the next slide, from the difference field I just showed you, wow, this is interesting. These are cyclones and anticyclones. There are 2 preferred pathways for TPVs out of their prison which is high latitude Arctic regions. Can you go to the next slide? Here's one of them. I don't know what happened here. This is the path. It's coming out, and where does this path lead? To the entrance of the Pacific Jet, which in stormy years is extended all the way to the coast, which means you're injecting these TPVs into the bloodstream of the circulation, preferentially in stormy years, which makes them stormy. And then there's another pathway out of the archipelago towards our slightly revved up subtropical jet over the Gulf of Mexico. So I'm interested in seeing whether or not there's anything to this. Is it really true that in certain years, once you have accumulated your nighttime generated, diabatically generated upper tropospheric features, do you differentially export them from year to year? And does that depend on how stormy the preceding month is? And then does it lead to a stormier spring? So I'm trying to understand something about the transition from the winter to spring circulation and how it differs from year to year. And that's kind of where I am on this. But it's kind of right at the initial stage. And Stephanie Henderson told me that this looks like some kind of teleconnection pattern, which I have to investigate more. So there's something kind of cool about that I stand to learn. So that's what I'm doing, among other things. But these are the kinds of questions that I stumble into and then pursue them. And for part of the time I'm in the pursuit, I kind of think, what the hell am I doing this for? This is dumb. And then other times I think, wow, this is really cool. So that's the joy of research. You never know exactly which one's right. So that makes it fun. So thanks.
All right, do you have any questions for John?
I know.
This is really interesting, John. My question that is arising from my very limited lens is that, Steph is right that this does look like a teleconnection pattern. So it quickly comes to my brain if there's any chance that you've seen that the stormy years happen to be when the tropics and the polar latitudes interact the most for an MJO or for El Nino or some kind of increased
I don't know. I have the years. We can take a look at that. I don't know yet. This is kind of the first increment of thinking about it, but that's a really good question.
Because this looks almost like the MJO teleconnection pattern.
Yeah, I wonder if that isn't it. Yeah. Brad.
Except that it goes over the pole. Most teleconnection patterns tend to stay in one hemisphere. The fact you've got one that actually goes over the pole to me seems unique.
Yeah, there has to be something internal to the mid-latitude that's changing it. Yeah. But it still also looks like there's something
Do you
have any student questions? Any other questions?
All right, thank you. Thanks a lot. Oh, that's just extra slides.
Great, so next up we have Dr. Brad Pierce. Brad Pierce is currently the director of the Space Science and Engineering Center here in the AOS building, where he works with global atmospheric models to explore atmospheric chemical composition and air quality.
Thank you. I think I can probably talk loud enough. So this is my lab. Two graduate students right now, Gerald Ogden and Maggie Bruckner, and a postdoc who's in the back, who's also part of my group that is now a researcher at the Space Science and Engineering Center. Next slide. So I'm going to take you on a trip from my field work in the last few years. I'm going to start out in 2017 where we were focusing on air quality along the western shore of Lake Michigan. I'm going to talk a little bit about fires in the western U.S. in 2019, and then I'm going to close out in some stratospheric work that we're doing. Just finished up the first deployment in February of 2022. And the key here is atmospheric composition forecasting from urban to global scale. Next slide, please. So to start out, we led a field campaign in 2017 that focused on ozone exceedances along the western shore of Lake Michigan. These are ozone design values. Basically, sites in red are an exceedance of the design value, which means that the ozone levels are high enough that it impacts public health. And you can see two sites, Sheboygan, Wisconsin, and Zion, Illinois. Not particularly populated areas, and surprising that these are where there's exceedances. This is a well-known phenomenon that's associated with the lake breeze front. This is a mesoscale circulation that's driven by temperature differential between the land and the water in the springtime. And we set up a field campaign with all sorts of measurements to explore this in more detail. what I've been focusing on the last 3 years now is modeling during this period and using these measurements to improve our ability to model these exceedances, which is important because EPA requires that the state of Wisconsin do state implementation plans to say how they're going to reduce these exceedances. Next slide. So this is just some results of this. Typically, when the EPA asks a state to do assessment modeling, they do this at 12 kilometers over the continental U.S. This does not allow you to resolve the kind of mesoscale structure that's driving ozone exceedances along the shore of Lake Michigan. And so we're doing very high resolution simulations at 1.3 kilometers that actually are able to capture the ozone and ozone production within that lake breeze front. So there's our high resolution depiction of the world from a modeling perspective. Next slide. And we can zoom in even further. This is some aircraft observations. We're looking at column NO2. You can see a smokestack, or the pollution from the Edgewater coal-fired power plant. And at 1.3 kilometers, we're actually able to resolve that individual power plant, its plume, and you can see this lake breeze circulation bringing that pollution onshore. Next slide, please. Next, we're going to go to 2019, summer of 2019, when we're in the field looking at western U.S. wildfires. Again, we're in the field to do flight planning, support, and Aditya Kumar and Maggie Bruckner were both in the field assisting in that. The objective was also to look at how we can improve our ability to forecast these fires. Here's an ensemble of different models that were being used in the field to forecast these fires. These are observations in terms of aerosol optical depth. Not going to talk about these in detail, but you can see that the models are all over the place. 2 of these models were ones that we had in the field, and since this mission, we've been doing work to develop and improve our ability to do this smoke forecasting. Next slide, please. So here's an example. This is a particular fire, Williams Flat fire, that was focused on intensively. Here's a simulation from our 8-kilometer continental U.S. simulation of the smoke associated with all the fires. This is with our standard emissions using the GOES geostationary satellite fire detection. And here's a simulation where we're actually using measurements of fire-rated power, or the energy released by the fire, for the emissions. And you can see this is aerosol optical depth. This is the flight track. You can see we've got much more aerosols from this fire in this optimized configuration. Next slide, please. Here's now a comparison of that same flight, except now we're comparing with airborne HSRL, or high spectral resolution LiDAR measurements of aerosol backscatter. So again, you saw the flight zigzagging through the smoke plume. Here's the sampling of that smoke plume over and over again along the flight track. This is our forecast where we just use the control emissions, and here's the forecast where we incorporated far-rated power into the emissions, and you can see we get much better agreement with the observations. This is work by Aditya Kumar that has been submitted based on this field campaign. Next slide, please. Yeah, isn't it big? But it gives you some idea about the amount of uncertainty in emissions right now. You saw in the first part of this the wide range of predictions from various fires. So that's at a very fine scale, particular fire. This is now work by Maggie Bruckner that's looking at this on a global scale. And here you can see comparisons between a global model prediction of carbon monoxide and from satellites, the Tropopause column carbon monoxide. This is the difference, and you can see that the model, in this case, global model, is over-predicting emissions here and under-predicting emissions here. So we still have a lot of work to do. Fire emissions are highly uncertain. Next slide. Okay, now I'm going to wrap it up. That was kind of our mid-scale continental U.S. look at air quality and forecasting. Now I'm going to go to the globe, and this is a very recent campaign. Gerald Acton, who's in the back of the room, and I provided flight planning and support for this SABRE field campaign. The objective here now is to look at transport chemistry and aerosols in the upper tropical troposphere and the lower stratosphere, in particular with regard to climate change and the stratosphere's sensitivity to aerosols. Flew about 6 flights. And this was during the time when the northern hemisphere polar temperatures were actually at their coldest on record in mid-February. And as a result of these very cold temperatures, we had ozone amounts within the Arctic polar vortex that were approaching the lowest levels that are on record. So interesting set of flights. We're just starting to dig into these. Most of what we have to show now is what we did in terms of flight planning. Next slide, please. So this is now our global model. So this is unlike the other models where we're looking at very localized air chemistry or continental US, now we're looking at global chemistry, and we're looking at it up much higher. So this is at 55,000 feet where the aircraft was flying to make these measurements. This is ozone on this level from our predictions, and this is nitric acid. The reason I'm showing ozone and nitric acid is basically polar ozone loss. First, you need to denitrify. You do this where the temperatures are cold enough that you can form nitric acid trihydrate. The nitrogen compounds sediment out of the air, and then you're able to activate chlorine, which destroys ozone. So this is now the depiction of what the circulation and ozone chemistry looks like in the upper troposphere, lower stratosphere. Next slide. Yep. This is freezing in on a particular day, the last day of the flight campaign. Here's where we're planning on going. We wanted to intersect this lobe of higher ozone that's peeling off the vortex with higher nitric acid. Next slide. And this is our flight planning track that we put together that we tell the NASA WD-57 where to go. It's one of the most exciting parts of being in a field campaign as a forecaster is you get to tell the plane where to go. So I'll stop there, take any questions.
So maybe, I didn't check, but I guess this spring is a high index dam, which would go hand in hand with a warmer spring, thankfully, here. Is that your understanding?
Well, it's been, again, it was coldest winter on record, but we're looking, you can see there's a pretty distorted polar vortex, so we're kind of having an early final warming. I haven't looked at it now, but yeah, those very cold temperatures are getting shut down, and as a result now, the spring, we're starting to get much warmer air getting intruding onto the pole, and I believe that we're now kind of in the midst of the final warming. But I haven't looked since I stopped forecasting on the 25th of February.
Today's 10 millibar seemed to shed that vortex to the southeast, and it's kind of reformed a little bit on the eastern hemisphere. It looks really robust again.
Okay, so it's reformed. Okay.
Yeah.
Anyway.
Do you have any other questions for Brad? All right, thank you again. Okay, so next up we have Dr. Ángel Adames-Corraliza. The Adames-Corraliza group studies the physical processes that drive large-scale dynamics and general circulation with a focus on the tropics.
Sure. I don't think it's necessary, but.
Right. We're all gonna leave here then.
That's okay. All right, good afternoon, everybody. It is a pleasure to be here. Like I said, it's great to see my group members, Rosa, Kayleen, Victor, and AC. We are moving down south towards the tropical regions. My research group mostly looks at tropical meteorology, tropical atmospheric dynamics. You can go on to the next slide. So it looks a little funky, but it's still holding up pretty nicely. So when you look at an animation of the tropics, you do see that there's all these thunderstorms and all these things happening, and everything seems like really chaotic and very different from what you see at higher latitudes with all the storm systems that make our day-to-day weather. You see that there's, in comparison, all these thunderstorms going on, and it looks like it rains a lot some days, and some days it doesn't. And you be inclined to think that it is random, but when you actually do certain types of analysis, you actually realize that all of this is actually controlled to some extent by these large-scale wave patterns that are moving around the equatorial tropical area. So this big blue stuff that's moving slowly, that mammoth is the Julian Oscillation. You got these things, these green things here called equatorial Rossby waves, and then this thing that's zipping along is called the Calvin wave. There's other things going on in there, but when you add these contours, you realize that there's actually these large-scale drivers that are actually, to some degree, helping the thunderstorms organize themselves, and then the whole system together kind of moves either eastward or westward, depending on the nature of the motion. By the way, this animation is on my website if anybody wants to download it and use it for their own selfish purposes. So, because of all these interactions, you know that there has to be some kind of interaction between like these large-scale waves, these systems, and the cloud systems that form them. So all these things must be interacting in some way or another, more likely than not in very complicated ways that are very difficult to understand and also simulate. This here is a diagram that I'm putting here because it never got published. So this is the version number 30 of a schematic that I made when I was in grad school. A version of this did get published. We ended up going to like version 71. Version 71 got published. This one was 30. I was really fond of this version, but my advisor thought it was unacceptable, so we ended up going to 70. So this is a Julian Oscillation. Look at all the clouds. If you're an observer, the anterior moves to the east. If you're an observer here, you see shallow clouds, then the clouds get deeper, it starts raining a lot, and then you get more of that anvil going on, and the winds change, and there's a lot of humidity. And it's a really, really stellar experience that I didn't get to see because when I was about to see one, I have to get evacuated. A great story for another day if you're interested in talking to me about nonsense. So next slide. So this leads to us to think that even though things are really, really complicated in the tropics, there have to be some major constraint as to what causes motions to behave one way or another. So this has led to several projects that not just my group, but other groups, both in this department and around the globe, have examined. And we now know that, for example, that water vapor, the distribution of water vapor around the tropical latitudes are very important for this organization of cloud systems and the waves that carry them. In fact, we actually know that there's a great diversity of motion systems in the tropics. A recent paper, actually is no longer in review, I have to delete that later. A paper that got published recently that I was a co-author on, we made this triangle of the different waves that exist in the tropics. So if you're a person that lives in the mid-latitudes, you know that Rossby waves are the troughs and ridges that control a good deal of the everyday weather that you see here. You got troughs, you got short waves, you got long waves, the whole shebang. And actually, in the mid-latitudes, you do get gravity waves and all these things. If you are amongst the people that's taking GFD with me right now, you might actually absolutely hate this right now, but you know, that's okay. You'll get to appreciate them one day. Waves are not a thing that you love from the get-go. So you have gravity waves up here. These are the really, really fast waves, and then as you go down, you get slower and slower, and then the Rossby waves are the slowest ones. So we know that these exist not just in the tropics but in other regions. So things get more and more unique as you move actually to the left here, and you get to this little corner here that's called the moisture modes. So moisture modes are kind of like the thing that's been gathering more and more attention, and it's a wave that exists particularly in the tropics, and as the name suggests, is driven by moisture. So it's essentially like a giant moisture wave that's moving around in the tropics. And you can imagine that mammoth that you saw in the earlier animation just being a giant bulge of water vapor that's just moving eastward with the waves as we speak. So you can move on to the next slide. So we know that these specific constraints like water vapor and the time scale that water vapor takes, it takes for like thunderstorms to kind of like eliminate the water vapor and move it around. These things actually make very, very large constraints on the tropical climate system. And in fact, they are such major constraints that we can actually use them to understand how the tropical latitudes are going to respond to climate change. And one thing that we have found, and this is from a 2018 paper that got a 2018 review paper, is that, for example, we know that as the climate warms, you go from this diagram on the left to this one on the right, and the first thing that you're going to notice is that this arrow becomes smaller, and that's because in the tropics, the stability of the troposphere has to increase, and that actually is such an important change that even though the thunderstorms get stronger, that stability effect actually wins out, and so the overturning circulation of the tropics has to slow down. And that has major implications to what you see up in the higher levels, because that means that anvil clouds, for example, these fake clouds here are going to get shorter, and also might have important implications to how the tropics teleconnect to the middle latitudes. So there's a lot of things going on in there in terms of what's going to happen with climate change. But the take-home message is that these like seemingly simple parameters, perhaps too simple to explain the whole climate system of the tropics, are able to give us something that we can work off in terms of predicting how the whole circulation is going to change with climate change. So next slide. So this is a summary of what my group does. So we combine kind of like a bit of theory, observations, and modeling. I don't run the model. I'm actually like almost like analphabetic when it comes to like running models, but I look at what other people run. So, but we do theory and observations. In fact, my postdoc Victor is kind of like observations supreme. He seems to like gather observations and like do it and like, you know, like a day or two is pretty amazing. Anyways, he's going to give a talk in a couple weeks, so if you're not a prospective student, you can come to his talk. Otherwise, I'll see you guys next year. And then we combine these three things to do exactly the predictions of the stuff that we do. So we kind of do a combination of everything, and that kind of keeps everything, everybody on their toes, because everybody's doing something in the tropics but very different. Cool, next slide. Yeah, so anyways, this is a slide tailored to the prospective students. If anybody wants to talk to me at any point in time, and you really want to nerd out with me and go to my office, we have looked at very specific disturbances and things that happen in the tropics. For example, the Julian Oscillation. We also look at tropical waves. My student Rosa looks at both African and Pacific easterly waves. They do really interesting stuff. My student HC Luo looks at monsoon depressions. Kayleen looks at tropical cyclone formation, and then we've had collaborations with people outside of this department and in this department about tropical convection, and then at some point in my life I did ANSO. I would like to come back to ANSO at some point. Maybe I'll write a proposal one day. Yeah, cool. Yeah. Oh yeah, you can go to the previous one just because there was a schematic that in it. Oh yeah, that schematic is really nice. This is a schematic of a monsoon depression, by the way. It was from my postdoc, and I'm really proud of it, so that's why I put it there. So. Any questions? No? Yeah.
I'll ask you a question. What is on the very first slide in your animation, what's the purple? What are the purple ones?
Oh, thanks for picking that up. So those are slow Kelvin waves. So like I made this animation at a time that we had like a specific interest a vested interest in understanding if the fast and the slow Kelvin waves are different. And I think they are kind of different, but like that paper got rejected and never published it. So yeah.
It happens.
On another schematic, Ángel, the one where global warming constrains the updrafts in the tropical convective plumes.
Mm-hmm.
Does that suggest that a warmer planet might sequester the tropics from the exotropics to a higher degree than is currently the case?
I am not sure, but I've been wondering if that's the case, and if that. So I went to a conference many years ago, and we had a conversation with somebody who did climate change, and our conversation concluded in that we were wondering if this means that there's going to be less predictability in the future, because there's a lot of predictability coming from these teleconnection patterns, and as these teleconnection patterns weaken because the upper level divergence is going to be weakening. We don't know if it's actually going to weaken. It could like not strengthen at all. That's actually still a lot of uncertainty there. But we think that because the mid-latitudes are going to warm, and because a lot more of the upward motion is going to be driven by convection, like more of these convective systems, and less stuff is going to be coming from these large-scale waves that are being forced from the tropics, that might cause like the two things to like separate more, but also become more unpredictable. I'm not sure. It's, I think, an open area.
Yeah, very interesting.
Yeah.
Any other questions? All right, thank you again.
All right, cool. Oh, yeah. Otherwise, I'm just going to keep walking away with this.
All right, so next up we have Dr. Matthew Hichman. Dr. Hichman's research explores the dynamics of atmospheric motions from mesoscale to global scale with a focus on the middle atmosphere and stratosphere-troposphere exchange.
Yeah, thanks for the nice first slide. That reminds me that here's Dan Forte. He's just started working with me on. We have a new index to look at potential vorticity variability at the top of tropical cyclones, and so he and Shelley Rowe and I are into trying to pursue that for an index of where in tropical cyclones is it most active in its development. Next slide. But today, well, this means there's going to be 256 slides. That's a fast faculty laptop. All right. I'd like to just describe three things that have come to fruition lately. The first is a study that actually took I've been working on it for about 30 years. The QBO direct influence on the upper troposphere and lower stratosphere. The second example is the origin of tropopause folds. It's a puzzlement for me for a long time, and I think in the last 15 years I've sort of come to a new perspective. See what you think of that. And then the last is a little bit of a different take on what a derecho is. I didn't really know much about them, but what I'm finding is kind of interesting. Okay, so here's the paper. It's an invited review talk in JMSJ, and it's about an observational history of the direct influence of the QBO on, this is a long list, on the tropical and subtropical upper troposphere and lower stratosphere. Why all that? It's because what we found is that the mean meridional circulation associated with the QBO is a latitudinal vertical integrator, extends all the way into the mid-latitudes. So what we did is analyzed westerly minus easterly differences in QBO phase and looked at seasonal geographical variations. The first study I did was in the year 2000, and I separated NSET data into these two time periods, but then we also used MERA2 data for this time period and ERA interim for this time period and got very similar results. So to show a couple of examples. But first, I should point out this important meridional circulation associated with the QBO. Chip Treffy, who came here to get a PhD with me in the early 90s, pointed this out to me that although we don't have quantitative evidence of exactly what these meridional and vertical circulations are, we know there has to be subsidence below QBO westerly anomaly. It has to be warm there from the thermal wind lock. And we know that there has to be return circulations on the side, but up until now, it just wasn't quantified. We also thought that there may be some sort of deformation of the tropopause occurring where there's an antiphased relationship during QBO easterly rising, cooling in the tropics, and at the same time, warming and subsidence of the tropopause region in the subtropics. So here's a comparison for NSEP, ARA interim, and MERIT-2. Each of them are by a slightly different method, but that's okay because these QBO anomalies are fairly deep enough. And you can see concentrations of this range over Africa, Indonesia, a little bit in Amazonia, not quite clear in that one, but more clear here. And the range is about 1.5 to maybe 2 degrees Kelvin or so. The tropopause goes up and down, and the temperature goes up and down. Further, you can see evidence in the subtropics for an opposing signal here. Next slide. Here's an example from the southern winter, and you can see a statistically significant result for the tropopause pressure in the subtropical westerly jet in the southern hemisphere. And then March, April, May was a bit of a surprise. Very strong signal. More zonally oriented than perhaps in January, but still stronger over Indonesia, Africa, and South America, suggesting some interaction with deep convection. And you can see the opposite phase resulting in the subtropics. And then here's an example for wind difference. And this is fairly striking too if you're interested in subtropical westerly jets, 3 to 5 meters per second stronger during QBO westerly. And then the water circulation in the upper troposphere is actually diminished. And then here's a long-term average of the circulation. First quantified representation of the QBO mean meridional circulation and its vertical and latitudinal extent, and how they fit in with temperature anomalies and zonal wind anomalies. You can see a 9-element tic-tac-toe pattern in temperature as these regimes descend with time. But if you know what's happening here, you know what's happening here and here and here. It's a latitudinal, vertically integrated pattern that extends at least to 40 degrees north and south, preferentially on the winter side. Let's just go back to the winter. So what you can see is if you have a temperature anomaly in the lower stratosphere for QBO westerly that extends forward and downward. Same thing with this wind anomaly here. Okay, thank you. So just some results. The QBO westerly favors a warmer tropical UTLS and a colder subtropical UTLS. There's a larger temperature signal near seasonal convective centers, which is consistent with both the temperature and wind shear causal hypotheses of the relationship between convection and temperature anomalies. There is a subtropical signal enhancement during the winter and in March, April, May, and both hemispheres. Just to fix ideas, QBO westerlies, we have enhanced subtropical westerly jets, and the Walker circulation is reduced. Okay. So for the second example, you're looking north here. There's a subpolar jet coming out here, subtropical jet here, and these are PV contours, and this is a jet flight path of sampling data which we analyzed. So the idea prevalent since about 1960 for explaining the sort of tropopause fold structure that's high PV under low PV is that there's some kind of circulation around the jet, which I was a firm believer in for the longest time. The problem is that when you look here and here, the vertical wind component is less than 5 centimeters per second. And so what I think happens is you have an previously in place high PV anomaly extending down to 4 kilometers. So this is actually stratospheric here. And it slid, say, down the 315K contour in the zonal mean from higher latitudes down to mid-latitudes of 4 kilometers. This was then overridden by air coming from the west, which was ejected out of thunderstorms, very low ozone air, juxtaposing high ozone with low ozone. Turbulent as heck, it's a mixing zone, but the constituent gradient is strong because of retraining from the tops of thunderstorms. So some conclusions, and I invite you to please read this paper and see what you think. Quasi-isentropic differential adduction can explain how tropopause folds are created. Also how jet superposition occurs. There's just one jet moving this way, and this other jet going like that, just differential adduction. The other main point of this paper, that strong constituent gradients are observed across the westerly jets are created by convectively injected boundary layer air with low ozone into the UTLS on the equatorward side of the jet. So this structure in low ozone, low PV, is outflow from thunderstorms upstream, just accumulated. Yeah, thanks. So this is a schematic diagram. East-west cross-section evolution here, plan view evolution here. You start off with a previously in place PV anomaly or trough at 4 kilometers. And then you have upper tropospheric air at 10 kilometers riding over it, and perhaps ideally doing something like that, yielding the classic structure of a tropopause fold without any circulation on the jet. So my last example is the famous Iowa ratio of August 10, 2020. And you can see it started in Nebraska, and after 12 hours it made it all the way to Indiana. And at 1600 it went past Des Moines. So here's the pressure rise in Des Moines in red. This is the duration of the cold pull. And the interesting thing is that the winds in blue were westerly, which you'd think the derecho should have westerly winds. As soon as that the gust front passed with an increase in gust wind speed, which is the maximum 5 seconds out of a minute, up to almost 35 meters per second, the wind shifted to the north. This is north-northeast. And what I found in looking at UCMWF data and UW-AOS simulations is that while the storm travels eastward, the momentum source for the outflow is actually coming from the north, which is really unusual. I didn't expect that. So next one. And to tie that together, what we have here is east-west cross-section. This is about 2 p.m. and it's in eastern, it's right about here. And we can see a updraft over a downdraft, which is what you'd expect. It gives a kind of a hydraulic jump pattern, and here's the cloud outline. And so this is sort of the geometry that you'd expect for a derecho. But the winds here are from the north, and the momentum, the zonal momentum, is actually higher just to the north than to the west. So then here's an interesting aspect, is that the updraft is associated with a positive PV anomaly and the downdraft with a negative PV anomaly. So you have this forward-backward horizontal PV dipole in the lower troposphere. It looks like this. What do you have in between? Well, you have to have a southward jet. And we think that that is why we have this pattern, is that the derecho is skewed by 500 millibar westerlies, but that the outflow is being tapped from a little bit north of that, associated with the divergent anticyclone below 700 hectopascals. And so that northerly momentum is just manifested here. And I thought of an analogy that might be bogus. You know when you have a snow machine and you can crank the funnel so it projects it off to the right and you go along, you leave a trail of snow off to the right. That doesn't happen to the north, it happens to the south. And so the outflow between this PV dipole, I believe, can explain this asymmetry of outflow, tapping into the northerly momentum in the anticyclone immediately to the north. And yes, the cold front is involved in this, even though derecho purists say that it cannot be.
All right. Do you have any questions for Matt? All right, so moving on to our final speaker.
Oh, yeah.
Okay, so up next we have Dr. Grant Petty. Dr. Petty's research focuses around radiative transfer and remote sensing, primarily in the microwave and solar bands, with a focus on precipitation rate retrievals. Did you want to use the microphone?
I'll try hollering. Can you hear me in the back? Okay, thank you. So the summary you just heard of my research is a little bit in the past, because my recent focus has been in very different areas. I did do a lot of work with precipitation retrieval over many years, and I decided to branch out fairly recently into a bunch of other things that have interested me for a long time. I realized I can't even possibly touch on all of them during the short time I have, so I tried to pick the two polar opposites that would most be incongruous in terms of how they're even remotely related to each other. And so the first, I'll talk about the project that we've had going for a few years to develop an ultralight airplane as a research platform. And then a new NASA-funded project that I'm starting, it starts in the summer, and they'll have a new student joining my group in the fall to work with me on developing a precipitation climatology over the global oceans, basically calibrating ship reports of qualitative weather occurrence in terms of, with the help of modern satellite-derived precipitation estimates. So that's the overview of where I'm going. They couldn't be more unrelated, really, but next slide, please. So basically back in 2015, 2016, I was having conversations with Professor Desai and others about how we really need to have an airplane in the department, because there's so many ways you need to get above the ground to measure things. It's a three-dimensional fluid we live in. Most measurements are constrained to be at the surface. Remote sensing is great, but it has its limitations. And you know, a lot of the things that are going on in the atmosphere are above ground, whether you're talking about the boundary layer or talking all the way up to much higher. But to get a conventional airplane of the type that people usually use for research, it's a very expensive undertaking, not only in terms of acquisition, but also in terms of maintenance and staffing, crew, all these things. So we decided to do something that was not quite as ambitious, but was more ambitious than a drone, because drones have their own limitations. They can go to 400 feet before you run into regulatory limitations where you need to get a waiver, and they can't go beyond line of sight without a waiver. And so basically what we did was we built a manned drone, if you want to look at it that way. And we had a couple of students helping us with the construction. We purchased the kit. I had support from a couple of fellow faculty as well as SSEC to acquire the kit. And we basically blasted this thing out in the summer of 2017, starting with tubes and using riveters and everything to construct this thing essentially from scratch, just from a box of tubes and bolts and things. there's the frame of one wing when it was completed and ready to be covered with fabric. I parked it by my car. I don't remember why I put it out there, but there it is. Next slide. So in 2017, I had my first significant off-field flight where it wasn't just doing crow hops down the runway. Go ahead and play it if you can. And that's at the end of the runway on a little grass strip in Verona. It's about a 20-minute drive away. Will it start? No. This should be an embedded video.
You can imagine, Brad. It's okay.
Well, I was going to show you the view that my wife hates to see because it shows my feet and then 1,000 feet of space between me and the ground.
If you get out of the animation of the full screen view, will it run?
Oh, I don't know.
I mean, it
Like
should run right on
sometimes
my
it does
computer.
weird things like that.
Oh,
like
yeah,
it
okay.
works.
What's going on with the
I
system
think the
here?
issue is that they ended up with Google Drive.
Oh,
That's
okay,
because
because this
it's
is,
called
yeah. Well, anyway, my wife refers to it as a flying lawn chair.
It kinda is.
But the thing that it has is the advantage, the ability to basically carry more instruments than a drone could carry in terms of weight. You don't have the limitation of line of sight. You can go above 400 feet. In fact, I went up to 2,000 feet on one of my more ambitious flights. It has some limitations in terms of handling wind and stuff like that, which we're learning about as we deal with these situations. Go ahead and take the next slide, please. And you'll have to step through from time to time. I'll show you what instruments we now have on it as of this last summer. So click once. So we have the instrument pod, which I installed, and I put basically drone-type hardware in there to monitor position and altitude and attitude and all kinds of other things, and also to provide guidance so I can navigate to various waypoints, just like a drone would. So you can pre-program a flight path and fly to those locations with direct guidance from GPS and everything else. Next. We basically took a drone-style temperature, pressure, humidity sensor that's self-logging and strapped to the wing strut. Next. We have a small sonic anemometer that we're experimenting with for true airspeed. And so we can use that, the true airspeed combined with heading and other information to get the winds. So next. What's coming up next? Oh yeah, we got a laser altimeter that tells us how high we are above the ground, up to about 600 feet. So we know exactly how high we are above the terrain. This all gets logged. Next. We have dual GPS antennas connecting to a moving baseline RTK GPS system that gives us heading orientation to high accuracy, which you need if you want to get the wind. So if you have the heading with high accuracy, combine it with the airspeed, and of course your translation from GPS, you can solve for the wind vector. Next. Oh, sorry, there's one more. And then for this specific flight, we strapped a 16-pound box in here, which is a sensitive device for measuring carbon dioxide. And we experimented with flying very low over an agricultural field to see if we could detect fluxes or uptake of carbon dioxide from the soil. Actually fluxes, because we were looking for soil respiration. But that was our very earliest first real science flight. And this was just last, I think it was October. I think that might be it for this. Oh no, I got a couple more. Next. Oh, anyway. And again, this is what I tell my wife that we have this ballistic recovery thing. So if I pull this thing, a rocket-powered parachute comes out, and the whole airplane comes to the ground in one piece, and hopefully be with it. It only works if you're about 400 feet, though, because otherwise it takes too long to deploy. Next. On a trial flight out to Sauk City, basically we went up to the agricultural research, dairy forage research site just north of Sauk City. Next. And left Verona. Next. Flew up to the airport there, got some more fuel, met some people, flew up to the next site. Next. It's about a 40-kilometer trip, so that's the longest time we've ever flown, or the longest distance we've ever flown from home, which was fun and kind of scary, I have to say, because it's a lawn chair. I was about 2,000 feet up the entire time. Let's see, and then study sites on their Cape. Next. So, capabilities and limitations. We're trying to develop this or demonstrate this as a flexible, low-cost, multi-purpose airborne research platform. It's not driven by a single science mission. We think it can do a lot of things. If you want to get something up in the air that weighs up to 10 kilograms, which we think is probably the upper limit, this would be better than probably some drones, many drones. I have no concerns about going up to about 2,000, 3,000 feet, which is a lot higher than drones will typically go or be allowed to go without a waiver. And I think 50 kilometers is probably the larger limit to how far I want to go horizontally, but 1 kilometer and shorter, you know, doing transects over a field for various reasons would be straightforward. And you have the flexibility. You don't have to ask anybody's permission. You don't have to hire a crew from somewhere. You just go out and fly. But no precipitation, VFR, no cloud physics. And it turns out this thing is really like a leaf. It doesn't like wind. So we're restricted in how much wind we can deal with at the surface. I found the hard way several times already. Okay, next.
Grant, does no precipitation mean fog too?
I wouldn't
Did
fly
you do fog
no.
studies?
I wouldn't fly fog, no.
There's a woman chair.
Yeah, go ahead and step through all, because I got a whole bullet list here.
That's the worst.
Sorry, Grant, what does VFR stand for? Is that like-
Visual flight rules, yeah, sorry.
Okay.
So I just realized I use up my entire time on just the ultralights, so. But anyway, these are the applications. We can imagine, anything you can imagine involves getting near from mapping, imaging, boundary layer structure process, radiant flux profiles, aerosols, trace gases, and micro to mesa scale, mesa gamma scale atmospheric structure are potentially things you could want to look at, and we're still trying to develop the opportunities to demonstrate these and show that this is something that could be incorporated into a field experiment. So I guess I'm out of time, all right. Okay, maybe one more slide just to show what. All right, so the other part that I was going to talk about that I won't is basically using GMI and other data from satellites to calibrate one more. Okay, I guess one more. Taking advantage of ship reports all over the ocean for 70 years and essentially trying to calibrate qualitative descriptive reports of precipitation to reconstruct precipitation patterns over the ocean prior to the satellite era in a way that literally is not possible by any other means. So I'll stop there. Thank you very much.
Do we have any questions for Grant? No?
Can we use the plane for like passenger flights to like increase department donations or something like that?
Random lawn chair?
So I would want to have my liability insurance up to date. It doesn't take passengers. Single person, it wouldn't get off the ground with 2 people because it's not powerful enough. What more would you like to know?
I could get department donations for a flight.
So maybe I could tow a banner over the alumni's house or something like that. They would donate for
Less than
that.
10 kilograms.
Yeah. Anything else? Brad?
But if you do find a student, their weight is important, and it increases your payload capacity.
I have literally lost weight
So you can-
to increase my overhead for carrying payload, in part because the plane turned out to be heavier than advertised, and there wasn't as much margin for payload as we had hoped. So, yeah, if I could get a student who's very lightweight and is not afraid to fly, knows how to fly, I'm still not sure I'd let them do it, but it would add up. It would free up some space or some weight for sure. Yeah. Thank you.
All right, thank you again to all of our speakers today.